Hey guys, so in today's lecture we are going to discuss power extraction from wind. So how we can extract the power which we required, that is electric power from the wind. So as we know that we can get the electric power from generator, and from generator we can get power from shaft power. So after converting the kinetic energy to the shaft power, we can get the the electric power. So as we know that wind turbines extract energy from wind stream by converting the kinetic energy of the wind to rotational motion required to operate an electric generator. So, we can get electric energy from wind. So it is assumed that mass of air which passes the rotor is only affected and remains separate from the air which does not pass through the rotor. So accordingly, as free wind interacts with the turbine rotor, it generally passes its energy to the turbine rotor, and the remaining energy due, which is left with the wind, that energy is low, and after transferring the energy, the speed of the wind also decreases to some a lower level. So as the speed of the wind is decreased, so that the trail, that leaving trail, that disturbed wind is called wake. So the variation in this velocity of the wind is considered to be smooth from upstream to the downstream, and it regains its value to reach the atmospheric level. As we can see in the graph, that as we can see in the graph that the velocity of the wind is greater, as we can see the velocity of the wind is greater. So hitting the turbine wheel, after hitting the turbine wheel, it reduces, and then it it will increase. Here as we can see that the pressure at the starting before hitting the turbine wheel is very high. After hitting the turbine wheel, it is reduced drastically below the atmospheric pressure, but after leaving the turbine wheel it will come back to its normal pressure. So here the variation is considered to be smooth from upstream to downstream. However, the fall in the static wind pressure is sharp, as shown here in figure, but the wind leaving the rotor is below the atmospheric pressure, but at far downstream it regains its value to reach the atmospheric level here again. So the rise in static pressure is at the cost of kinetic energy. So this rise in static pressure is at the cost of the kinetic energy, consequently further decreasing the wind speed. So here the pressure is increased, but further the speed is decreased here. So here further the speed will of wind will decrease due to increase the pressure. So the velocity then also increases again to its initial value far behind the wind turbine, and the widening of the stream tube disappear. So this velocity will also increase to its original value after a long far behind the wind turbine. So after very long distance, it will reach to its initial value. So this is the concept of pressure and velocity when the wind will hit the turbine rotor. So now we will see some mathematical steps and calculations to find how much power can be extracted from the wind. So here we are considering a horizontal axis propelled type wind turbine. Okay, so this is general wind turbine. So here let A be the inlet plane, B be the exit plane, Vi is incoming wind velocity, Vi is incoming wind velocity, Pe is wind pressure at exit, Ve is wind velocity at exit, Pi is incoming wind pressure. So and V is specific volume, that is 1 by rho. Okay, so this is the various symbols which we are going to use. So here VE is less than VI. Okay, so exit velocity will be less than inlet velocity. We are assuming that. So applying total energy equation, as we know that U1 internal energy plus P1 V1 plus V square by 2G, that is velocity head, Z static head, and first pressure head, plus delta Q, that is change in heat, similarly pressure, velocity, datum head, and work done. So here, as the level is same, so Z is equal to 0, and U internal energy is also 0, and P into V, uh, that is flow energy. Here there is no heat and work done, no heat is added, no work is done, so Q and W is 0, and G is taken as 1 meter square per second. So here our total energy equation will be P1V plus V1 square by 2 is equal to PA into V plus VA square by 2. So here PI is inlet pressure, PA is inlet plane pressure. Okay, so here as we have discussed that there will be total 4 planes, that is inlet A, B, and exit, that is outlet. So here we are considering total 4 plane. So here first plane, here we are considering this first plane. So here P1 P Pi into V plus Vi whole square by 2 is equal to PA V plus Va whole square divided by 2. So here, as dividing the whole equation by dividing the whole equation by V, that is volumetric specific volume, that is V specific volume. So here so P1 V by V will be P1, then V1 Vi square by 2V, and similarly on the right hand side. So as we know that 1 upon V is equal to rho density. So here we have shifted in numerator, and we got 1 upon V is equal to rho density. So similarly for exit area, we can consider that PE is equal to rho VE square by 2 is equal to PB plus rho VB square by 2. So here we have considered for inlet area, this is for inlet area, and similarly we have considered for exit area. Okay, so the wind velocity decreases from A to B because kinetic energy is converted to mechanical work, as we know that. So in rotor from A to B the velocity will decrease. So VI will be greater than VB and VB will be greater than VE, and similarly PA will be greater than PI and PB will be greater than will be less than PE. So this is the relations of velocity and pressure. Now what we will do is, let's consider this equation as number 1 and this equation as number 2. So subtracting number 1 equation from number 2, so and making PA minus PB as subject. So this PA minus PB we are making subject. So what we will get is, we will get PA minus PB is equal to PI plus rho VI square minus VA square by 2 minus PE plus rho VE square minus VB square by 2. So assume that at exit velocity from the turbine at E, we assumed that pressure PE will be PI. So at exit velocity, suppose we are considering that pressure we are getting back, so that exit pressure is and inlet pressure are the same. So we are considering PE is equal to PI, and also that VT is equal to VA is equal to VB. So we are considering that here in between the velocity in the rotor are almost same. So what will happen, that here PI and PE will get cancelled out, so we are left with rho as a common, and also VA and VB will get cancelled out. So we are left with PA minus PB is equal to rho into VI square minus VE square divided by 2. So this is the pressure difference equation, that is difference between the pressure in blade, that is PA minus PB. So if A is the area projected in the wind turbine perpendicular to the wind stream, so how much area it is projecting. So suppose we are considering as A, then the force, actual force will be is pressure into area. So what pressure we have found here, so we will multiply this with A, then we will get our actual force, that is P into A. But actual force also equal to the change of momentum, but we also know that axial force is equal to the change of momentum. So what is the formula for momentum? So momentum formula is m into v, this is mass into velocity. So therefore, so delta m into v we are considering, so change of mass into velocity, product of mass into velocity change. So as we know that mass m can be written as rho a into v, that is density m can be written as rho density, area, and v velocity. So instead of m we are writing here, that is rho a vt into vi minus ve. So Now, comparing both the equation of force that we have got, that is pressure into velocity and change of momentum, comparing both the forces, so what we are getting is rho av into vi square minus v square divided by 2 and rho avt into vi minus v. So now cancelling out rho a, and as we know that a square minus b square can be written as a plus b into a minus b, so that we have written here. So vi minus ve will get cancelled out. So what we have got is vt. What is vt? So vt is generally the average of, it is vi plus ve divided by 2. Okay, so which is inlet velocity plus outlet velocity divided by 2. So now considering the total thermodynamic system bounded by inlet I and exit outlet E. So so W is equal to kinetic energy inlet minus kinetic energy outlet. So this is the state, the how much work we have gained, that is inlet kinetic energy minus outlet kinetic energy. So how much kinetic energy is transferred to the wind. So by subtracting the inlet minus outlet, we will get how much work is done. So let's, the power P is defined as rate of work done. So we will multiply by work energy into mass. So we will get the power P. So that is P is va square minus v square by 2. So now similarly we can write mass is equal to rho a vt into va square minus v square. So here again we can write vt is equal to vi plus ve by 2, and here a square minus b square can be written as a plus b and a minus b. So we will get, so here we will get that vi plus ve and va square minus ve square. So this is the power which we are getting from the wind. So when we can get the maximum power, so this is very much important point, that which we want, that how we can extract maximum power from the wind. So to get that maximum power, we need to differentiate this equation with respect to exit velocity. So we are differentiating this equation with respect to exit velocity ve, that is dp by dve is equal to 0. So here for differentiating, so these terms are constant, so it will doesn't matter, so it will be 0. So what, which terms are there? So here there are two terms vi and ve. So after sorting this out, so we will get that 3, after differentiating it, we will get 3ve square plus 2 ve vi minus vi square is equal to 0. So how we can get this? So if you multiply this equation, that is vi with if we multiply these two brackets, so what we will get is, first is vi cube, so then we will get minus 2 vi ve square, then plus ve vi square, then okay, so wait a second. Here if we multiply this two bracket, so what we will get is, so first we will multiply it by this, so we will get VIQ. Then second we will get is, sorry, minus sign, with a minus sign. So with a minus sign we will get VI into VE square. Then with a plus sign we will get VE into VI square. Then with a minus sign we will get VE cube. So we will get VEQ. So if we multiply, so now if we differentiate these terms, so what we are getting is, so differentiation of this VI cube will be 3 VE square, sorry, so we are differentiating with respect to VE, so sorry, so we are differentiating with respect to VE, so differentiation of VI cube will be 0 as it is a constant. So differentiation of this 3 VE cube will be 3 VE square. Then the differentiation of VI into VE square will be twice VE into VI, and the differentiation of this will be just VI square. Okay, so here we got our equation after differentiation. Then so after differentiation, taking the terms common, so we are getting 3 VE minus VI as common, so into VE into VI. So by solving this we are getting that VE is equal to VI, and so as this is the second power equation, so we'll get two answers. So first is the value of V, we are getting VI, and V is equal to 1 by 3 VI. So as this is only the practical possible acceptable solution, because the exit velocity cannot be equal to inlet velocity, so this is not possible. So the only possible solution is that the exit velocity should be 33.33% of inlet velocity. So at this velocity only we can get maximum power, optimum maximum power. So using this in the equation of power, so we will get the maximum power will be equal to P max is equal to 8 by 27 into rho A VI cube. So here in the previous equation, that is what previous equation we got, here in this equation we are putting the value of VE is equal to 1 by 3 VI. So here we are putting 1 by 3 VI. So after putting that value we will get the maximum power, that is 8 by 27 into rho A VI cube. So ideal or maximum theoretical efficiency will be, that is maximum power divided by total power. So as we know that total power is 1 by 2 rho A VI cube. So here the maximum efficiency which we can get from the wind turbine is known as 59.3%, and this is known as Bat's limit. Okay, so this efficiency is this limit is called Bat's limit. So it is clear that the maximum efficiency of propeller type wind turbine is 59.3, and we cannot go beyond this limit. Therefore it is known as Bat's limit. So in next lecture we will see forces on blades and thrust on turbine, and we will see some numericals. Thank you very much.